Right, and I think most of you would have had some prior knowledge as it relates to radioactivity. Anybody can give me an idea as to what we mean when something is undergoing radioactivity or some radioactive decay kind of stuff? Anybody can tell me what they remember from, maybe fifth form or even maybe in your chemistry class, I don't know. But you can either use the chat feature to just give me an idea as to what that is related to. Or the question might be then, why does, you know, um, elements undergo radioactivity? Can anyone answer that?
Sir, because of its instability.
Because of its instability. What makes an element you know, unstable? That's it. What makes an element unstable? Can anyone answer that? What makes it unstable?
Sir, an unfavorable proton to neutron ratio.
Which is right, yes. Right, yes, so that's one factor as well. And also, the heavier the element becomes, which speaks to, the unfavorable amount of protons and neutrons, that will pretty much determine whether this element will undergo a radioactive decay, right? And I think within that process, you should know by now that whenever something undergoes radioactive decay, an element is released or some type of stuff is released, and we're going to look at those things, right? So it's really me. Radioactivity is really centered around elements that are too heavy. You understand? If they're too heavy, then the chances are they are going to become unstable, and then they want to reach a point of stability, so they're going to break, or we say disintegrate to a certain amount. If you can remember anything about that binding energy thing that we looked at, where we had the curve looking like this, right? Right, and you would have had maybe uranium on this side, and we said that uranium would be able to can undergo a fission, procedure, which is basically taking a much heavier element and breaking it into smaller daughter, nuclei until it reaches a point of stability, which is somewhere around iron, right? So that is what is really happening here, right? When it comes down to, radioactivity for the most part. We should also be able to can sketch a graph like this, which pretty much shows the binding energy per nucleon, right? And this is the number of nucleons, right? We went through this in last term, so you ought to be able to can draw this, because I've seen questions where they ask you to actually sketch it and so forth. And we know that going this way is a fission scenario, right? And obviously going towards iron, that's going to be fusion. We looked at that recently. So let's just go and see what this thing has to say to us. Now, so nuclear instability, right? From time to time, you'll have elements that we can consider them to be, elements that are really heavy. And when that happens, they become unstable. I mean, it speaks to a lot of things. You understand? I was going to make mention of something, but I won't say it, right? So, if you have a lot of things going on in your mind, right, chances are you will be an unstable person. Good? So please try not to have a lot of things going on in your mind. You'll become unstable, and chances are you might, disintegrate. All right? Now, so with that being said, a process of radioactivity occurs whenever you have an instability nucleus, right? And for that reason, we say that it breaks down into, daughter nuclei, and in that process, some amount of energy is released, right? Massive amount of energy. So as you can imagine, when you look at the fusion and the fission experiment for the most part, I mean the fission one, that speaks to more of a nuclear radiation thing taking place there, where you're disintegrating the element, right? And as you can see, one of the byproducts would have been energy, right? Now, the stability of the nuclide depends upon the number of protons and the number of neutrons it contains, right? I don't know if you remember anything about when we were looking at that video about the island of instability or stability, right? And those guys who were making those elements and so forth, they would have to carefully put in certain amount of protons and neutrons and all of that kind of thing to, make the element become stable, right? So all of those things right there comes into play. Now, we have been talking
Sir,
about
can I talk about this?
the breaking down of an unstable nucleus, right? Now you're going to hear us talking about a terminology as such as radioactive decay, right? And we want to be able to can define that. We must be able to can speak to what radioactive decay speaks to. So we will move right into that as soon as your classmate is finished there. But anybody, I think we're on the same track, right? Are we understanding what we're talking about here so far? And I should make mention of the scientists who, pretty much did some work as it relates to radioactive decay and radioactivity on a whole. You have persons like Henry Becquerel, right? Becquerel, I think that's how it's pronounced. Henry Becquerel. He's one of those persons who pretty much was a founding father of radioactivity. Then now further on, you're gonna hear about I think it's Marie Curie, and other persons there who did some amount of work as it pertains to that. So if you see those names ring a bell, maybe in a
Sir, I can change.
all right. If you see those names ring a bell in a multiple choice question, then you know that it's of those persons are the persons who did some work as it pertains to radioactivity and so forth. Now, radioactive decay, right? It's a one of the things about radioactive decay is it's a random process, right? Which means that you cannot predict when a uranium-238 is going to disintegrate, right? You cannot really predict it. So that's one of the things about radioactive decay. But you're going to write this for me in terms of the definition. While I have it here to say that it's a random process, meaning, you can't predict it, I needed to write this definition for radioactive decay. So radioactive decay is the spontaneous and the random process whereby an unstable nucleus attempts to become stable by disintegrating into another nucleus another nucleus, and one or more of the three ionizing radiations, and one or more of the three ionizing radiations. Do we have that?
Yes, sir.
Right. So as we said, no, we must be able to can define radioactivity. We don't know when they can ask us to do these things or to define it, but we should be able to can define it. And as we said here, it's a random process. It's very spontaneous, means that you can't tell when it's going to happen, right? And that is just when an unstable nucleus, right, would disintegrate into or to attempt to reach a point of stability. Because in nature, things always want to go back to a state of stability. If you push something over, chances are it wants to go back to a state of equilibrium and so forth. So that's the same thing when it comes on to radioactive decay. If you have an unstable element or nucleus, it will always want to reach to a point where it balances. You understand? And I think that's how we are as well, right? So with all of that being said, now because the fact that radioactive decay is a spontaneous process, right? Now, what we're going to come to understand is that from time to time we want to find what we call the constant of decay probability, right? So this is almost like guessing when that decay is going to occur. While we say it's random and we can't predict it, but we can use probability to pretty much tell when it's going to occur, right? And that is now going to be dependent on the amount of the element that is present, right? So based on the amount of element that is present and the time that it is lapsing by, you can pretty much predict, or to not say predict, but to get a probability of how the decay is taking place over time. And with that being said, we're going to hear us talking about what we call either the decay constant, or you can hear we say the constant decay probability. From time to time, we want to find that different elements will have a different, constant decay probability. So from time to time, depending on the element, we'll want to figure that out. And in order for us to figure that out, we have to come to this consensus right here. Right? We have to come to this consensus to pretty much figure out what your lambda value, which is the decay constant, is going to be. Now, how you define the decay constant? The decay constant is really that probability of the nucleus decaying per unit time. So that's how you define the decay constant. Now it says that this value can be calculated by finding the change in the number of nuclei, right, of a sample over time over the initial number of nuclei. So at first, this equation is coming from this to say that delta n over n, which is basically finding that probability, right, dividing by that by the change in time, would basically equal to minus lambda. All right. So, but what we do, we just kind of rewrite it in a sense to just make it look a little bit more, what do you call it now? What can I say? I would want to say a little bit more linear in a sense, because what you realize is that depending on the amount of the initial amount of nuclei, right, that will basically determine and or affect the overall amount that is going to be disintegrated. Because if you start out with a much larger portion of n, then you can expect that the decay process is going to take much longer. right? So it's just to show you that this equation here is just really showing you to say that depending on what your initial amount is, and if that is much larger, then obviously this overall thing over here is going to be a much, it's going to be directly proportional, which is basically the remaining amount that is left, so to speak. All right, let me see here. But let me know if you guys are following though, so that I can know. All right. Another way how we could write this, rather than using the triangle, we could say dn over dt is equal to minus lambda times n. Right? You see that the minus here just speaks to the fact that that there's a disintegrating process taking place, right? So that's the reason for the minus sign. The minus sign is just show you that the amount is going to decrease over time. You understand? So that's what it's just showing here. So if you see the minus, it's just telling you that what you start out with is not what you're going to end out with. It's just showing that there is a change going on right there. All right. Now, we're going to derive that this formula that you're seeing here. This is the real formula. It's coming from this, what we just looked at here a while ago. We're going to derive it very soon, but I just want you to understand that whenever we're dealing with radioactive decay, there is a specific formula, and it came from that one a while ago, that dn upon dt equal to minus lambda times n. It came from that, but we're going to derive it very soon. But if you see this anywhere, this is basically that radioactive decay formula. And whenever we see a formula like this that involves some exponent, then it means that it's going to be, whenever you plot the graph, it just shows us that this is going to be an exponential decreasing graph based on the nature of this equation. So at all times, whenever we see anything that deals with E, it shows us that this is the graph that you would pretty much get. And it makes sense to say that if you start out with 1,000 nuclei of an element per se, right? As the process, as time continues, right, that element is going to decrease, right, from its initial amount, some remaining amount and all of that, right? So just bear this equation in mind. We're going to derive it. It's going to involve some integration and all of that, but we're going to go to that process very soon. But yeah, note that N, this big N right here, is basically the remaining nuclei, right? So it's the remaining number of nuclei, and not is the initial amount of nuclei, because obviously you'd have started out with some amount, right? We know lambda already as the decay constant, and as we said, that decay constant it varies in terms of the element that you're disintegrating. T in this case speaks to the time. Okay. So we'll soon derive. I think that's the next thing we're going to derive. So bear in mind these graphs. We're going to look at these graphs in more, because there are other things that we want to talk about when it comes down to these graphs, which you will see eventually. But in order for us to derive that equation that you just see, and from time to time you can be asked to derive it.
Sir,
right?
can you go back, please?
There you go. So we when it comes down to deriving certain formulas and so forth, we can't neglect it. Please don't neglect it in going into your exams and all that, right? Never you neglect the derivation of while it might be hard to remember some of them, you just have to probably put in the work and try to remember how it was derived. Okay. And what you can also try to use to remember when it comes down to these equations, right? If you remember anything about X-ray attenuation, it's the same format of the formula that it has. When an X-ray beam is fired at something, right? The intensity of it is going to disintegrate over, depending on the thickness of the material that it is passing through, right? So if you remember that equation would start out by saying, I is equal to I naught, right? E to the minus mu x. I believe that's the formula, right? Which just pretty much kind of show you a similarity. They don't, whenever you're dealing with an exponential graph, the format really doesn't change much. Whenever we're dealing with capacitors, right? The format of our discharging capacitor, it doesn't really change. We either have Q is equal to probably Q naught, right? E to the, I think it's going to be minus T upon RC, right? So the format really doesn't change by much, right? So, once you kind of remember one for discharging, then you can automatically remember the others. You understand? As a matter of fact, in some cases as well, whenever
Okay.
yeah, man, I know. There are times when we want to perform, you see, a radioactive decay experiment. You will see where we can use capacitors to pretty much, simulate the process. All right. So because of how the graph is going to disintegrate in a capacitor when it is discharging, we can say, all right, if I don't have a radioactive substance, then it means that I can use this to simulate the experiment. Okay. Or in some cases, you will see us, if we were in the lab right now, we would use a titration experiment as well to pretty much do the decaying process. We don't have radioactive substances, which I'm pretty happy that we don't. All right, so to derive this formula, right, the radioactive decay formula, we're going to start out with the same thing that we had on the first screen that we talked about that says, dN upon dt, right, is directly proportional to n. So that rate of change in the nuclei is directly proportional to the initial amount that we started out with. Okay, and we'll just put that minus sign here, as we said, to just pretty much show that the process is disintegrating. Now, because we have a directly proportional relationship going on here, there's automatically a constant of proportionality. Our constant of proportionality is going to be our decay constant. So we can then restructure our formula to say that, all right, minus dN upon dt is now equal to my decay constant, lambda times n. Now, for this, what we're going to do next, we're going to separate the variables, meaning that I'm going to group the n's by themselves, and I'm going to put the t's by themselves, or the dt on one side. So this is what we're going to do. So by separating the variables, we get minus dN upon n, right, which is now equal to lambda times dt. As a matter of fact, let's take the minus sign as well. I'm going to take the minus sign across. So there's a minus sign here. Now that we have this, we can sort of simplify this by showing you that 1 upon n times dn is equal to, minus my decay constant times dt. I do this because of the integration process that we're going to do next, right? And I'm pretty sure that this doesn't affect the price of rice. It's the same thing. If I were to just take out this fraction right here, it doesn't affect anything. So the next thing that we would do is that we're going to integrate both sides. So integrating both sides of the equation, and I think we know the integration sign, so we'll go ahead and put this right here, that integration symbol. So we're integrating 1 upon n with respect to dt, not dt, dn, and we're then integrating, minus lambda by dt. Now, because the minus lambda is a constant, right, which is almost like a number or anything of that nature, we're going to pull it out in front of the integration symbol. And I think you guys who do math know that already, right? Because any constant, it's not going to be affected in the process here, so we're going to pull that out. So when we do pull that out, we're going to take out the minus as well. So we have minus lambda integrating by 1 of dt. And of course, we can write back this side to say the integral of 1 upon n by dn. Right? Now, this is where we're going to integrate now. I think you guys know that when you're integrating 1 upon n, right, that is going to become ln n, right? Let me know if you know. So whenever you're integrating 1 upon n with respect to dn, this thing here, when you do the integral of that, it becomes ln n. And I think you should know by now, if we're integrating 1, that is going to, with respect to t, that 1 is going to basically become t. So what we're left with is minus the time constant, right, by the integral of 1 with respect to dt, which is now t, okay? And I think, I don't remember the complete math about it, but we have to put a plus c right here, right? We have to put a plus c. But in this case, we're not going to completely need the plus c, but we're going to just put the plus c there for that purpose. So we have that. We have all of this now, right? The next thing that we're going to do we are going to do, give me a second here. Yeah, so we want to get rid of ln on the left hand side. In order to get rid of ln, we have to basically times it by e, because ln and e cancels out. So since ln and e cancels, we're going to basically, times that on both sides, right? So we're saying that e and ln is going to cancel out, leaving us with, give me a second here. Yeah. So that ln and e is going to cancel out. So we can cancel that now, leaving us with n, right, equals to e raised to the minus theta times t. And of course, this e is also going to pretty much, the e in the c as well. So we're going to put a plus e c. Plus ec. Now, because c is going to equal to 1, in this case, right? because c is going to equal to 1. Let's put something in our calculators. E raised to the 1 is what? No, let me check. All right, don't do that. Don't do that. Give me a second here. Okay, I see where I went wrong. I should have put in the limits. That's where I went wrong here. All right, follow on this part, guys. So you see right where we had the integral sign, right? And you know, we had dn upon n. Put in the limits right here. There has to be two limits, which is, you know, speaking about the, because whenever you're integrating, there's two limits. There's an upper limit and a lower limit, right? In this case, our upper limit is going to be n, which is pretty much the remaining amount. So that's like the final thing that we would have. And your initial amount would go here, which is going to be n naught, right? So put in those for me, where you see that in the that you were writing down a while ago. Similarly as well, for this part, you need two limits, which in this case, because we are the time would have started at 0 for the disintegrating process, right? And throughout the process, then you would have had an upper limit of t time. So you have to put that upper limit there, because with integrating, you have to have limits that you're integrating within. All right. So just make that adjustment to that formula or to the equation. So you can also make note. I have less than a minute, so I'll restart it and pick up from here. Right. So please put in the limits. So the limit, as we said, is pretty much speaking to the amount that you started out with and the final amount that you now have. Because when the process is disintegrating, you would have started out with n naught, and at the end of the process, you would have left with n. Similarly, if you're starting the radioactive process, the time at that point is going to be 0. When you end the radioactive decay process, you're going to have a time of t. So we have to factor in those limits. So when we do the integration now, right, of 1 upon n with respect to dn, that's going to become ln n, and based on the limits now, I have to factor in the limits. So by factoring the limits, I basically get a subtraction in a sense, where I'm subtracting the upper limit from the lower limit. All right, that's how the integration works. So at this point, I have ln n minus ln n naught. Now, using the whole laws of logs, right, I think we should remember by now that if I have ln of a divided by b, we can write it as to say ln a minus ln b. that's a rule in logs, right? Whenever you have that scenario, you can basically expand it by saying this. So just like how we're seeing ln n minus ln n naught, I can simplify it by saying ln a divided by b. So let's just simplify that. Let's just simplify it. So when I simplify it, I now have ln, right, in bracket n divided by n naught, close the bracket, that is now equal to minus the decay constant times t. Now this is where the part now comes into play about the ln and e cancels out, right? So since we know ln and e cancels, then we can e both sides. We can e both sides. So I'm saying e times ln in bracket n divided by n naught, close the bracket. I'm e in this side, so I now have e to the minus decay constant times t. So this cancels out. So what I'm now left with is n divided by n naught equals to e minus my decay constant times t, and then I can further simplify this by saying n is now equal to n naught e to the minus decay constant times t. So this is how we would derive this equation. Okay, this is how we would derive it. Let me know if you have any questions for me. Remember that's an exponential equation. Let me know if you guys finished taking it down or what. And as I said, this is a proof that we can get from time to time. So don't neglect it. If there's any question, you can ask it now. Are we good to go? Can I next it? All right, that sounds like a yes. Okay. So that equation that we just came up with a while ago, as I would have shown you already, that this is what it would give you if you were to plot a graph with all of that information, right? So ensure that you can sketch the graph to show that this speaks to, when you have n is equal to n naught e to the minus, t, decay constant times T. So this is your graph, just showing you the, and by the way, on this axis is where you would have had N, right? Because N is the remaining amount, and of course on this axis you will have T. Now based on where you start, right? Based on where you start, that's where your N naught value is going to be, right? That's where your N naught value is going to be. We have that. All right. Now another thing that comes into play here.
Sir, excuse me.
Yeah, go ahead.
Can you go back, please? Okay, sir. Thanks.
All right, yeah. So another thing that you'll hear us talking about when it comes down to radioactive decay is a thing what we call activity, right? Activity, and that just speaks to, you know, the number of nuclei that decay per unit, or decay per second. So if you see the terminology decay, I mean not decay but activity, it's just talking about the number of nuclei that would have decayed, you know, within maybe 1 second or so forth, right? And with all of that being said, it has its own equation by itself, similar to the one that we just derived a while ago, right? We can also use this to talk about a radioactive decay process. So rather than using the amount of nuclei, right, we're now considering the number of nuclei per second, which is what we call the activity of the radioactive substance, right? So just bear that in mind to say that, you know, you can have two things that we can use to describe a radioactive decay process. We could have used the raw in terms of the amount of nuclei, initial amount of nuclei, or we could consider the amount of nuclei per second, which is the activity. Now, in just the same way, we had a scenario where, you know, delta N upon delta T was directly proportional to, you know, N. It's the same thing that is happening here. So the activity, depending on the initial amount, right, or the number of nuclei that is present in the sample, that will determine the overall activity of the element. So if you have a lot of this, if you have a lot of N, right, that you're starting out with, then you can expect that you're going to have a lot more activities. Versus, you know, if you have less of the amount that you started out with, then you're going to have less activities taking place. So there's a directly proportional relationship. And for that reason, we can come up with this formula to say that A is equal to the decay constant times N, where N speaks to the number of nuclei in the sample. And we know that lambda speaks to the decay constant, or the constant of proportionality. Right, so as I was saying, that we can use the whole activity concept to speak to, you know, a radioactive decay. And for that, this is the equation that you would use if you wanted to practically or simulate, you know, what is happening when you have X amount of nuclei per second, which is the activity, right? So obviously you would have started out with your initial activity. That is when nothing would have disintegrate. But as time lapse, you would expect that the activity is going to decrease, hence why you would have had this type of graph. So if you were to draw a graph, right, of activity versus time, then you would still have a exponential decreasing or an exponential decay graph showing this type of scenario. Now, the thing about activity, it has a unit. Remember when we were talking about Henry Becquerels, right? The unit for activity. So if you're saying that the amount of activity that is remaining is, say, 40 whatsoever, then you have to say 40 becquerels, right? So just bear that in mind, that it has a unit as well. Okay. So all these little formulas that you're seeing here, we ought to know them, because we could use this to find out the initial amount of activity, providing that if we know our decay constant and we know the initial amount of nuclei that is present in this sample, then you can find the activity of that element, right? So that's an equation that we can use from time to time, right? And we can also use this one here, you know, to find certain information that we want. We're going to look at how we use it eventually. And I must let you know that with all of these exponential equations, we can get a straight line graph from it, as you would know, similar to that of the capacitor equation, similar to that of the one that centers around X-ray attenuation. We can linearize all of these equations to find, more than likely in this case, you would linearize it to find the decay constant. We're going to look at that eventually. But before we go into that part of linearizing those equations, right, another concept that comes into play whenever we're dealing with radioactive decay is what we call the half-life, right? And it's very simple. You understand? It's nothing complicated, right? It is just the time that the radioactive substance takes to reduce itself by half of the initial amount. So if you notice, you start off with 1,000 nuclei, right? Then your first half-life is going to be when that 1,000 would have disintegrated to half of the initial amount, which would have been 500. So on your graph, you can find your half-life by just looking to see, all right, if I start off with 1,000, then obviously when I reach 500 and extrapolating the graph, the time corresponding on the x-axis would be your first half-life. On a decaying graph, you can have multiple half-lives. You can have multiple half-lives, as you can see here. So the next half-life that you would consider would be from the 500, right? So your initial amount now is 500. So from that 500 to the next half-life, that would be obviously 250, because half of 500 is 250. So that would be your second half-life. You see what I say? Then now your third half-life would be when that 250 has now disintegrated itself by a half. And as we can see, you just extrapolate right across here to find that third half-life. And it continues. There are several half-lives that can occur on a particular graph, up to about, I think the amount might be about 6 or so, right? In a regular decaying process, you can have that amount of half-lives. You know what I say? Now, the beautiful thing about half-life is that it is constant. What it means is that if the half-life from 1,000 to to 500 is say 2 seconds, then when the second half-life occurs, it's also going to be 2 seconds. All right? It's also going to be 2 seconds. So that's what that is what we mean by when we say that the half-life is constant. All right? So yeah. So as we said, we can use the graph to find the half-life. We can use the graph to find the half-life. We can also use the equation to find the half-life. We're going to show you how we come by that in a sense, and to show you how you can use the equation to find the half-life. All right. Yeah. So this right here is the linearizing of the graph of the equation that I was talking about a while ago. That equation that says n is equal to n naught e to the minus wavelength, not wavelength, minus decay constant times t. So as I said, anytime we see an exponential equation, it can automatically be linearized. And I think you guys, some of you know how to linearize equations, some of you don't. I think some of you should pay attention here. It's nothing hard. What you're essentially doing is you're seeing an exponential decaying equation. Chances are you would have to get rid of the e in the equation, which is just basically, taking the ln, because we know that ln and e cancels out. So we'll be basically multiplying both sides by ln. All right? It's almost similar to what you would have done to derive the equation. You would have canceled out the ln to get the equation. It's pretty much the same thing. You're just doing the reverse here to get rid of the e in this case. So as you can imagine, if I were to take this equation and ln both sides, then you would have ln n times ln multiplying by ln naught. Let me say that again. So ln n is equal to ln, and this ln right here is multiplying everything in the bracket. So you would essentially have ln n naught plus ln e to the minus lambda times t, right? Whenever it comes down to log, as you can see right here, the information is here. If you have a multiplication of logs or ln, then it means that you can break it into addition scenario. So wherever you see multiplication, right, laws of logs say that we can break it and add them together, right? So that's what you would have seen occurring in this step 2 right here. So this was the first step, right? This ln is multiplying everything. Now we're using the laws of logs to break it apart. When we break it apart, we get ln n naught, right, plus ln e to the minus t, or minus lambda t. This is where now ln and e cancels out. So this one is going to cancel out. And when that occurs, you're now left with ln n equals to ln n naught minus lambda t. All right? Minus lambda t. In some cases, you will see this in some mathematics book where we say, all right, ln e to the minus lambda t. We can take this and bring it in front. It won't affect the price of rice. That's another law when it comes down to logs. To say that if you have something in the power, you can take it and bring it down almost like a constant in front. So you will see this is how it makes sense now. So if you have minus lambda times t ln e, simply now ln and e cancels out, then you're now left with this in the pretty much in the numerator of argument's sake, right? So this is how we get this now. And all we want to do here now is to rearrange the equation in such a way that it is in the form of y equal mx plus c. You should know the variables that's going to be plotted on your y-axis and what is going to be on your x-axis, right? In this case, ln n, that is the variable that would be on your y-axis. Good? And of course, time is going to be the next variable. So that will obviously go on the x-axis. Now we know that the equation of a straight line says y is equal to mx plus c. Now whatsoever is beside x, we know that that is going to be representing our gradient. So in this regard, my gradient m is going to be equal to minus lambda. So that is how we can find out what the decay constant is by linearizing the equation. So if I say use the graph to find lambda, I don't have to tell you that you need to find the gradient, right? You should know by now to say that, all right, if I linearize the equation and compare it, I can automatically see that my gradient is going to equal to minus lambda, right? Because they're in the same position. And if I want to find, if I did not know the amount of initial nuclei that I started out with, then this is where your C value, which is your y-intercept, comes into play. Y-intercept. So what if I want to find out how much nuclei I started out with? Then all you would have to do from your graph, which would be an exponential, well, not an exponential, but it will be a negative straight line graph, right? So on this side we have ln n, and we have t on this side. So the graph will look pretty much something like this. Now, wherever it cuts the y-axis, you can clearly know that that is going to be your c value, and c is going to equal to ln n naught. Good? We know already that, by finding our gradient, that is obviously, your y2 minus y1 divided by x2 minus x1. Good? So once you find the gradient m, then you can say, all right, my m value is going to equal to minus lambda. Okay? Now, you see, guys, I want to say something to you, see? And I see it where whenever you're doing, like, exams or you're plotting graphs and so forth, if the question says use the graph, right, to probably say find the decay constant, right? It don't necessarily mean say you must take two values from the line, you understand, and put it into the linear equation and then transpose to find m. I know that it really means, right? In this case, it means to say the gradient you have to use. You have to use the gradient, right? Because what you're going to realize is that if you just use a y value and an x value and your y-intercept, it's not going to give you the accurate value for m, because your gradient is like finding an average in a sense, right? So if you limit yourself to using 2 points only, or to say my only 1 point in terms of y and x, then it's going to affect the m value. So don't use the equation if they don't ask you to do that to find lambda. If they ask you to find lambda, clearly it means that lambda is related to the gradient, so you have to work out the gradient from the graph to find the value. You understand? So don't pick a point and put it in the equation to say, all right, ln n is 10, and you say, all right, minus lambda, and wherever 10 corresponds, you put the t value, which is 2, plus the c value, which probably might be what you call it now, maybe 5 for argument's sake. We don't want you to do this. You understand? We leave that to the math class and so forth, but not in ours. Right? Any comments? Let me know if you understand what I was saying just now.
Question, sir.
All right, good. All right.
So you're saying we shouldn't plug in the values for y, c, and x. We should find the gradient. Get 2 points and find the gradient.
Precisely. Exactly so. Right? Okay. So we have to pay attention to those details, because that's where you lose the marks now and then. Because I'm pretty sure everybody knows how to find the gradient, right, of a graph. So if you don't go ahead and do that, then that is where now you're gonna lose the mark. You understand? And when you do this, what the thing that you would have done here wouldn't give you the accurate value as it pertains to finding the m value or to find the lambda value. You know what I'm saying? So as much as possible. And I think for your exams that is coming up, right, you're going to get something related to this where you have to linearize it, and not only linearize it, but to do other things as well. And I'm going to clear the screen to just kind of show you the extent as to what we're talking about now. So imagine now, I think we understand how we would have found m or find the decay constant by using the gradient. And I want you to understand as well that whenever you see a line going down like this, right, it means that the gradient that you calculate from this line is going to be negative. All right? Any line looking like this going down like that, it's going to be, the gradient for it is going to be negative. So always bear that in mind. If you have a graph that looks like this, the gradient is going to be positive. I think some of you would understand that. So clearly, my gradient here is going to be negative. So if m is negative something and we have minus lambda, then these negatives will cancel out, which just shows us that my decay constant is not going to be a negative number, right? It's going to be a positive number. So if you see indicating a negative number for your decay constant, chances are something is incorrect, all right? Now, what if I want to find my my initial amount? We said that C, which is your y-intercept, corresponds to ln n naught. So all I would have to do is to say that ln n naught is equals to C. Remember, we want to find n naught. So all I would have to do now is to multiply both sides by e, because we know e and ln cancels out. So multiply both sides by e, which I'm going to say, all right, ln e times n naught is equal to e raised to the c. E raised to the c. So ln and e cancels out. So now my n naught is now equals to e raised to the c. All right. On your calculators, right? You see the button where mark ln. If you look above it, you see one e and you see one x. I don't know how your calculator look, but just be mindful that the e that you're using here is the one that you would have to press shift ln to find that e, and then you put in the c value, which would come from your graph. So you either read by your graph what the c value is, which is your y-intercept. That y-intercept value is what you would put here, so to pretty much find the initial amount of the nuclei of the substance. You understand? Man.
Sorry.
Therefore, hold on. Yeah, man, let's do that for me. Hopefully that's how I can deal with it. Go ahead now.
Yes, I came off a while ago. So what up? You're transposing or C?
We're trying to find the initial amount, which is n naught, because that's another thing as well. You see, sometimes I don't know about the KF exam has changed a whole lot, right? So the easy questions that we normally get one time, we might not get them again. Because sometimes they would say, all right, tell us what is n, tell us what is ln, n naught, tell us what is lambda and all those things. But I don't think they're really doing much of that anymore. But we must remember that n naught is the initial amount and n is the remaining. Okay? So what I was just doing just now, what if the question presented itself to say that I want you to tell me the initial amount of the substance? Then you would have to use this portion of the linear equation information to find that out. So we're saying ln n naught is equal to c because it corresponds when you look at it from the y equal mx plus t equation. And let me just write this again. So ln n is my y value, right? Minus lambda is my m value. T is my x value. And then whatsoever is here, that ln n naught is my c value, which is my y intercept. Good? And so, with that being said, if I want to find n naught, I have to equate these things to say ln n naught is equal to c. To find n naught, I would have to multiply both sides by e, because we know ln and e cancels out. So ln and e cancels out, leaving me with ln naught equals to e raised to the c. This is something that you also have to remember as well, that the c goes in the power. All right? It goes in the power. I was also making reference to how do you find that e. You would have to go on your calculator, look for ln. If you look above ln, you see e, ex. So you press shift and press ln to get that e that we're talking about. It's not the exponent that you see down here, but it's that e right above the ln sign. And once you put in the c value, which you would have gotten from the graph, right? So just remember that the c comes from the graph. The c value is where your y, where the line intercepts the y axis. And from this on, you just put in the value and you find the initial amount. You understand what I'm saying? You see what I'm going now?
Yes, sir.
All right. So this is typically, how to look, in a sense, for the most part. Those lines that you're seeing going up and down there, I think you know that those are the error bars. But you would not be really you're not really need to put that in and all of that in this case, right? But and guys, I mean, I don't understand some of you. Like when it comes down to a thing we call the line of best fit. I think the word line of best fit speaks to what we ask you to we ask you to draw. If we say draw a line of best fit, then it means to say it must be a line that best fits the trend of the data. You go in an exam and you draw a line that is not a line of best fit, you just lose the marks right there, then and then, and you would have calculated your gradient beautiful from that lovely, foolish line that you would have drawn, and it would have affected everything else that you would have needed to do, right? So you have to always remember that when you get a line like this, or we see something like this, and you know it's a linear thing you need to draw, you must be drawing a line of best fit that fits most of the points. You understand? That is something where you're happy have rooted and grounded inside of your system. Now, there are times when you will have points that are far away, which is what we call outliers. If they are outliers, you don't involve them into the line because it probably just speaks to the fact that there was a blunder, there might have been a systematic error, those kind of things, right? So now try to force the line through the last point or, the point that is way off, right? Keep it within the trend of the data because you want to interpret the trend of the data. If you draw something all the way like this, if you draw something go down like that, right? Trying to catch it to this point, it's going to throw you off. When you try to find your gradient, and all of them something there, that's how come it's going to throw you off. You understand me, I say? At least, guys, try to, whenever you join the graph or you have the points, if you realize, say the points, them zigzag and all of that, right? Try to make the line be balanced on both sides, meaning that equal amount of distribution in terms of the points that did not pass through the line. try to make it even. So if 2 over here, so make 2 up on the other side. You understand? And draw your line through it. This is not exactly how it looks, but I'm just saying to you, right? If you have 4 over here, so it's unbalanced. So you can't afford to lose the mark because of that. Just because of that, when you can just simply rearrange the line a little bit to get a better graph. You see what I say? Those are the things that will mash you up. But less than a minute, so I'll just restart it and pick up from where we we need to go. All right, let me see now. As it pertains to this thing here, there's something. This graph is not necessarily the exact thing. Something is off with this in a sense. In terms of the equation, not sure what's happening here. Right, so something is not completely correct here, but don't focus on this. I was just trying to get a graph that looks like this. All right, so don't focus on this equation. Something is a little bit off about that. Yeah. Okay. So remember when we said, let me just wait a little bit. So guys, I pray and hope that you don't make small mistakes that could give you your marks on the exam. You understand? Whenever you're probably doing a graph question or something of that nature. As I said, the CAPE exam has changed, right? They I don't know how to even describe it, but they want you see everything what you learn like from probably in a grade 1, you understand, all of those things is coming back to apply, you understand, simple little things, right? They how to even read a simple graph, how to find the smallest box in a graph. Those small things are some of the things that they are asking us these days. You see, you guys wouldn't got you never. Let me check something. So you guys did your first CAPE exam in 2020. So you would not have gotten a chance to do the paper 2 to see what it's like. Your paper 2 these days consists of 3 questions, right? It's a very tricky thing because how it's structured, right, is that no, I mean back then, when you get a regular paper, you would have had the opportunity to choose, not to choose, but you're getting a variety of questions. Because generally the paper was structured in 2 sections. You have section A and you have section B. Now, with the first question in section A, that question is normally a module 1 question, right? The second question in section A is a module 2 type question. The third question is a module 3 question. Now for section B, the first question in section B would also be a module 1 question. And the same thing applies all the way until you finish the entire paper. Now what they have now done is to, and I must say this, back then the first module 1 question would be a different question in section A, and in section B it would have been a different question. Now for the revised exam that they now have what they did is to take the module 1 question, and put them together. But by putting them together, what it does, it limits the amount, not the amount, but it limits the range of possible questions that you guys could have gotten for module 1. So it is now kind of crammed into one area, one subject, not a subject area, but one area of the syllabus in a sense. So if it's talking about, let's say, capacitors, so question 1 is going to be purely about capacitors. So if you never know about capacitor, then dog, name your supper. So you'll probably just lose the marks for that first question. And what if now when you go to section the second question, it has something where talk about operational amplifiers, and you never know about operational amplifier, then dog, name your supper, because there's no other question related to module 2 that you will be getting again to sort of like give you a better edge in a sense. So, and the same thing for module 3, it's going to be about one question and all of that. So it's a little bit more harder in a sense. But what if you understand what if there's a part where you understand that question completely, then for you, then that's good, right? But you just go for sure, say, you have to can apply yourself in all areas, right? Because it is no longer an option in a sense where if you never do good for the first module 1 question, then the second module 1 question in section B, you could have maybe get a chance, because we know that the syllabus is very lengthy and all of that. So maybe in some case, like talking about the old paper now, the old paper probably would have something on resistivity for the first module 1 question. Then the second module 1 question probably could have been something about magnetism, which you could have see yourself through. But no, the first question, if it's related to magnetism, the question depends, right? And so it continues. So you just have to be mindful of that. Okay. And it requires a lot of thinking. It requires a lot of thinking, right? Okay, yeah. So as we were saying now, as it pertains to Half-Life, we know Half-Life as the time taken for half of the initial amount to be remained, right? So having said that, we can use the linear equation, right, to basically find the half-life, and this is what we're going to do. So imagine that our equation says n0, and sometimes they ask you to derive this as well. So n is equal to n0 e to the minus lambda t. Now at half-life, what it means is that the remaining amount, which is n0, is equal to a half of the initial amount, right? So this is the concept here to derive that formula for half-life, because there's a formula we can use to find it. We can use the graph to find it, but what if you don't have the graph? Then you use the formula. So having said this, because n is equal to a half of the initial amount, then I can go into this equation and put to say that n is equal to half of the initial amount. So half of the initial amount, which is n0, is equal to n0 e to the minus lambda t. Now, we can clearly see that n0 and n0 can cancel out. So once we do that, what we're now left with is a half, right, equal to e raised to the minus lambda times t. By the way, this t right here is the half-life that we're trying to find, all right? So just bear that in mind, so that this is really the half-life, or the time, that's the half-life that we're trying to find. A half-life is a time value, right? So that is what we're trying to find. So for us to do that, we now have to pretty much, we want t to become the subject. And in order for us to get t as the subject, t is in the power right here. So we have to then put some ln thing into practice. So we have to ln both sides. So we're ln in both sides. Let me see the time as well. All right, cool. We have enough time. So we have ln a half, all right, is equal to ln e raised to the minus lambda times t. Cool? Having said all of this now, we can see that ln and e cancels out, or before we do that, we should bring this down, bring the power down in front of the numerator, or in front of the ln e, yeah. So we're going to bring that down. So I'm going to write the rest of it over here. So to say ln a half is now equal to minus theta times t, right, times ln e. We know ln and e is going to cancel out, so we can cancel that out. So we are now at this junction. But before we can even go any further, we must do this. We must expand this fraction here. Because remember, we said that whenever we have a fraction, we can rewrite it as such to say that ln 1 minus ln 2. So we have to do that. So once you do that now, we're now equating it to minus the decay constant times t. Then, if you put in your calculator, what is ln 1? ln 1 is equal to 0. So 0 minus ln 2 is equal to minus my decay constant times t, which is this t is the half-life that we're trying to find. And so we're now saying, we can even go ahead and say ln 2, but we don't have to put that yet. So we can say, all right, we have minus ln 2 is equal to minus decay constant times t. We know minus and minus cancels out. So we're saying now ln 2 is equal to decay constant times t. I want t by itself, which is my half-life. So I divide both sides by my decay constant, which now leads me to say that my half-life, which is, you can write it as this to say capital T with a subscript half, is equal to ln 2 divided by your decay constant. So guys, if you know your decay constant, is it? Give me a second. If you know your decay constant, and so once you know your decay constant, you can literally find the half-life easily. But if you don't know the decay constant, there are ways you can find the decay constant. So this is just another equation that you must put in the back of your mind, not the back of your mind, but the front of your mind, right? Or you must have it in mind to say that if I want to find my half-life, I can say ln 2 divided by my decay constant. You could have derived it as well, because you must remember that at half-life, it's when half of the initial amount is remaining. And so it means that n is equal to a half of n naught. And you just derive it from there. So you can actually derive this as well. Okay? So this is that formula for calculating a half-life. Are we good? I know we have a lot of silent people in this class, right? But it's okay. It's very fine, right? But yes. There are other ways though, how we can consider finding the half-life, right? Let's just look at this question. It says that a sample contains a million atoms of iodine, iodine, right? it says that how many atoms of iodine, right, is going to remain after after this amount of days, after 8.05 days, how many is going to remain after 16.1 days, how many is going to remain after this amount of days. So in my guess, I'm thinking that the first half-life, you see, it's a very simple question. I think what this is just showing us, this is the first half-life, right, which is 8.05 days. So all they wanted to do is to just see how much is going to be remained at the end of this, half-life, which is pretty much 40.25 days. Which we know that there's no such a thing about 40.1 or 40.25 days. We know that there's not a thing like that, but it's just to just put it in practice. I think this 0.25 can be calculated in terms of minutes and seconds and all that. But yeah, so if you start out with this amount, a million atoms, right? And we say, all right, the first half-life for that is 8.05. Then the remaining amount at this time is going to be 500,000, which is 500,000. Then our second half-life, remember we said that half-life is a constant thing, meaning that it's incrementing by the same amount each time. So that's the reason why the second half-life would have been 16.1, because you'd have to times your first half-life by 2 to find the second half-life. So 16.1 days. So when 16.1 days occurs, I must have 250,000 of my iodine remaining. See? Now, my next half-life is going to be, let's just check. So 8.05 times 3. So the next one are going to be 24.15. And of course, you're just dividing the 250,000 by 2. So you get 125,000. That's the remaining amount there. The next half-life I got be now. Let's see. That is 8.05 times 4. That's going to be 32.2, and that is just dividing this number by 2. My bad. This is going to be 62,500. So that's the amount that is remaining on that day. Then the next half-life now are going to be when you reach to the 40.25. So if we take our first half-life, which is 8.05 times 5, that's where you get the 40.25, which tells us now that the remaining amount is going to be half of this, right? Which is going to be 31.25, right? So at the end of the day, at the end of the 40.25 days, this is the remaining amount, all right? And another thing that they can ask you from time to time.
Sir.
Yeah, go ahead.
So how did you know that 8.05 was the first half-life?
Because that's the first time that they give us here. So like, I think they should have stated it, right? But it just goes to show though that, and even if we didn't know we could use these two first numbers to figure out to say, all right, that is going to be the half-life overall, because from 8.5 to 16.5, that would be 8.05 in between, which would just signify that, because remember, so the time constant is half-life rather. Half-life is a constant value in between, right? So, you could use those values to just say, all right, obviously the first half-life would have been 8.05. I know it's hard to just look at it and say that's what it is.
Sir, so you won't use the formula?
No, you can't use the formula here because you don't know the decay constant. You couldn't use the formula because you don't know the decay constant. No, you see,
Okay, sir.
that formula would just tell you the half-life, right? It wouldn't tell you the remaining amount, as you can imagine. But you don't know the decay constant for iodine, so it wouldn't make sense to use that. Okay. So there's no set formula that we use to do this. You just have to consider, say, all right, I start off with 1 million, right? If you start off with 1 million, the time is going to be 0. But as you disintegrate it, right, you would expect, give me a second, guys. All right, yes. So, this is kind of like a much easier way to write it out in a sense, because you don't want to make it look a little confusing and so forth. So you're taking that guess that this is the first half-life because that's the first time that they gave you in terms of the days, and then you're just decreasing this by a half each time because that's how half-life is situated as. To say each time you're decreasing the remaining amount by a half, and this would have been 16.1 days. Then the next amount is this amount as it will be remained for the next half-life, which is going to be 24.15. So as you can see with the question, they did not give you what we say now, the in-betweens right here. So from 16.1 to 40.25, they left out some of them. So you don't have to make sure you say, work out everything. I think there's a formula. that you can use. Let me just see if I can bring it up here. There's a little formula, There is one. But, there is one small formula here. I saw it somewhere at one point. Yeah, it's this thing in a sense, right? So if I wanted to find, this is the same question, by the way. I took it from the book, right? Let me see. Yeah. So we could have simply jump ahead, and pretty much find out the remaining amount at the end very simply by you saying, all right, the initial amount times 1 divided by 2 raised to n. But the trick about this, you might not have known that you would have had five half-lives. You might not would have known that you have five half-lives. So from here, this is 1 half-life, 2, 3, 4, 5. So there are 5 half-lives. So by using that equation that says, 1 million, which is the initial amount, right, times 1 divided by 2 raised to n, where n speaks to the number of half-lives. So if you know the number of half-lives that are that were involved in this overall scenario, then you could have used this in a sense to find out the remaining amount at that particular number of half-lives, which is 5. So I would have put 1 divided by 2 raised to the 5, right, times that by the 1 million, it would have given me that 31,250, right? I don't know if you remember this, but if you can just simply do it like this, right? Then you won't run into any problem. But this is, I guess, is just a simplified way of doing it. You know, I don't know how we can remember that, but you see what we're at, guys? I think you guys are seeing and understanding what we're doing so far. No, guys, do something for me. You see, just use a textbook. Use a textbook and review this information here so you can see a better understanding of it in terms of what you're saying and all of that. And also, you can attempt a one or few questions as it pertains to the decaying of a sample. So like a question like this right here that talks about cobalt. Jada, this is your mark on the screen a while ago. Yeah, so.
Hush, sir. Hush.
Okay. All right. See that, so a thing like this, you could try a question like this. You say, calculate the initial activity. I don't like these questions, I don't like these questions because don't try this yet. I when I talk about carries as yet, because carries is the unit for it's another unit that we use as well. So don't touch this as yet. All right. But we're gonna get some questions pertaining to that and all of that. Some possible questions sooner than later, right? But please ensure you guys are reading your books and all of that. And I said to you already, you see, whenever you study, use your syllabus. Your syllabus is your study guide, right? So it outlines to you what are some of the things that you must be focusing on. So when you look on the syllabus now, right? A typical question that you would see coming on a regular paper would say, question could start off by saying discuss the use of radioactive isotopes as tracers for carbon dating and in radiotherapy and so forth, right? So you have to be able to can discuss it. So if you're going through the syllabus and it says to you, use the relation that says that the half-life is equal to L2, right? Ln2 divided by this. It means that you must be able to can use it in terms of applying the question to solve problems. You see what I say? Then when you look at this part now, it says that describe an experiment to determine the half-life of a radioactive isotope with a short half-life, which more than likely we're going to look at radon because that's probably the one that they recommend. So you must be able to can describe it. You see what I say, guys? So let's give you some tips and ways that you can help your own self. And when I go up on the internet, go check off things and pull in information where you really don't need at this point. You understand what I say? It's supposed to explain activity. Well, the activity is basically that the amount of nuclei per second. So you must be able to can explain that. Explain what a decay constant is, right? Explain what is a half-life. That's the reason why we put those definitions and so forth on the thing. You see what I say? So your syllabus is kind of like some of the things where you would generally, it says write the equation for a radioactive isotope. The syllabus is not the best of syllabus because they never tell you to linearize it, but at some time they might ask you to find things from it. You understand? So this just gives you a guide as to what you need to know for the exams and so forth, right? Relate radioactivity to nuclear instability. That's where I started from, to show you that elements that will be unstable because of the fact that they have different amount of protons and neutrons and all of that, and what happens when that occurs. A spontaneous decay occurs, or a spontaneous thing happens of what we call radioactive decay. All those things, right? So please, it says right here as well, sketch the exponent nature of a radioactive decay. So it means that you must be able to can sketch it. You understand? So when we put the information on the slides, we go through the syllabus and we say, all right, syllabus said this. So we put it there, to say you must look on it, you must kind of have an idea of what is this about. No overlook it at no point. You see what I say? So we're getting down to the wire now, where we have to kind of like start putting things together. See? So guys, just pay attention to those things, and think we can have a successful future. You know, it might have been rough at some.
Sir,
Go ahead, please.
sir, but I want to know, is there a set time for the mock exam?
Okay.